Dear students, I have the pleasure to take you through our second video on the topic experimental design. Today we shall be looking at principles of experimental design. Remember from the previous video I introduced experimental design, and I said basically a number of research work in biological sciences involves a situation where the researcher has to lay down an experiment whereby you manipulate some of the factors which we refer to as the independent factors, and then observe what happens to the dependent factors. So now, but this is not just done in an organized manner. So what I'm going to introduce today is what we refer to as principles of experimental design. Principles of experimental design. And I'm sure we all understand what the word principle means. These are standing issues that must be respected. When we say, that is my principle, it simply means that no matter what happens, I will always respect that. So when we say principles of experimental design, whenever you are designing an experiment, these are standing rules, or I don't know whether I should call them guidelines. They are supposed to be respected. You must make sure that you respect these principles. Those must be respected. Right? Now, what are these principles? There are basically three basic principles of experimental design, namely replication, blocking, and randomization. So when we say what are the principles of experimental design, I expect you to be able to say, no, the principles of experimental design are replication, blocking, and randomization. In other words, an experiment must have replications. It must have blocking. There must be some form of randomization. Of course, there is an exception where you may skip one principle, for example, blocking, as you are going to see as we proceed. But that cannot just be done all over. So there are certain situations where you can skip, you can ignore one of the principle. So here we are saying, whereas the first two helps to increase precision in the experiment, the last one is used to decrease bias. So in other words, replication and blocking is meant to increase precision, but randomization is to decrease bias. But one would ask, what is replication? What is blocking? What is randomization? Let us proceed. Randomization is the random allocation of the experimental units to the treatments or factor levels. That is very, very important. From the previous video, I indicated to you what experimental unit is, what are treatments, or what are factor levels. Remember, treatments, they are different states within a factor. That is what I said. And the experimental unit is that which is receiving a treatment. And then you measure or you observe how the dependent variable will react. So you make measurements on the experimental unit. You observe the behavior on the experimental unit, the behavior of the dependent variable. So by randomization, we are simply saying the allocation of the experimental units to the treatments, it has to be a random process. Now, this can be done using random numbers or statistical packages such as the GenStat. There is a package called GenStat, that is general statistics, which is used in biological research to analyze data. So that GenStat can produce randomized treatments. Of course, the researcher will have to put some parameters to it. Now, its purpose is to remove bias and other sources of extraneous variation. You see, these are new terms. Extraneous variation is that variation which is caused by a factor which is not being investigated. That is extraneous variation. It's sort of an intruder, a factor which we are not interested in, but it has the potential to influence our response variable or the dependent variable. So we need to get rid of this extraneous variation by allocating the experimental units to treatments or factor levels in a random manner so that we remove what we call systematic bias or researcher bias. Another advantage of randomization accompanied by replication is that it forms the basis of any valid statistical test. As you are going to see as we proceed, a lot of statistical tests such as analysis of variance and so forth, especially most of the parametric, we call them parametric tests, they make an assumption that the errors are random. So how do you make errors to random? You make errors random by initially making sure that the experimental units are allocated using a random process to the treatments or factor levels. So randomization is meant to eliminate bias, to ensure independence among observation. This is very, very important. Required for valid significant tests and interval estimates. Okay. Now, do you see what is happening here? In each pair of plots, although replicated, the new variety is constantly assigned to the plot with the higher fertility level. What it means is that, suppose this is our plot, a single plot, this one, starting from there up to the end in this manner. Now, if you look at this plot, suppose we've got an old variety and a new variety which must be allocated. We don't want a situation whereby a new variety occupies only this region, going this direction, from here up to here. If our study is to compare the performance of the new and the old variety, we don't want the new variety or the old variety just to start from here and go in this direction. That will be wrong. Why? Because you can see that the comparison is already biased from the onset. The new variety is already given high fertility zone, which is this zone here. This zone here up to the end. So to avoid that, we want a situation whereby at least we have got new, old, new, old. Each of the variety must at least occupy the high fertility zone and also the low fertility zone, so that the response is actually due to the fact that we are using an old and new variety, not the intruder of the ground where the variety is grown. Now, what is replication? A basic experiment is the one in which only one experimental unit is assigned to each treatment. Replication is the repetition of the basic experiment. Now, let me just give a very basic example to help you to understand what we talk of when we are saying replication. Suppose we have got four athletes who are competing in a 100-meter race. So let me assume that we have now our four athletes. They are in these tracks. Athlete 1, athlete 2, athlete 3, and then finally athlete 4. They are racing in that direction. Now, this is the winning point, W. So if we record the time that each of these athletes will take to reach the W point, of course, the shorter the time, the lesser the time, the faster the athlete. So what happens is that if they run once, we call that a single replicate. We can actually make a decision on who is the winner. But when it comes to experimental work, we don't want just a once-off trial that is a basic experiment in which only one experimental unit is assigned to each treatment. We don't want that one. So we want a situation whereby they run first, we record, they come back, they run, that is the second replicate, we record, they run again, the fourth replicate, the fifth replicate, and then we get the average time taken in order to determine the winner. That is the basic idea behind replication. So it is the repetition of the basic experiment. It is the assignment of at least 2 experimental units to each of the treatments whose effects are under investigation. Now, it allows the accurate determination of the experimental error, improve the reliability of the estimates of treatment, and sensitivity of statistical tests. This is very, very important. You need to know what replication is. It is repeating the basic experiment. A basic experiment is the one in which only one experimental unit is assigned to each treatment. But we don't want just one experimental unit assigned to treatment. We want several of them so that at least we get an average in order to increase the precision or the estimation of the experimental error, thereby improving reliability of the results. Now, each treatment is applied independently to 2 or more experimental units. Yes. Variation among plots treated alike can be measured. Increases precision. As n increases, error decreases. This you are going to see. Remember, the standard error is actually a function of n, where we are dividing by n, so where n is the number of replications. So this is what we have here. Now, what does this mean? Standard error of the mean is equal to sample variance over n. And I want you to take note that the sample variance is always constant. It will be constant, but this is what we need to increase. So when you divide by something very big in a constant value, what we get is something very small. So the standard error of the mean will become lesser or lower because when we increase the number of replications. But it must be understood that as we increase the number of replications, we are actually incurring costs. So increasing the number of replications means we need more resources in order to run several treatments in an experiment. So we need a compromise between cost and accuracy of the experiment. It broadens the base for making inference. Smaller differences can be detected when you have a number of replications. Now, what determines the number of replications? Do I sleep and dream about the number of replications? What determines how many replications should I use? Pattern and magnitude of variability in the soil, number of treatments, size of the difference to be detected, required significant level, amount of resources that can be devoted to an experiment. You don't increase replications to so much when you don't have resources. Limitations in terms of cost, labor, time, and so forth. Even the land size when it comes to agricultural experiments also is a determining factor. Now, what are the strategies to control experimental error? Select appropriate experimental units, increase the size of the experiment to gain more degrees of freedom, more replicates or more treatments, Error variance will increase as more heterogeneous material is used. So it may be self-defeating. That is a cautionary statement which I have to give. So select appropriate treatments. Factorial combination results in hidden replications, therefore, will increase n, which is the number of replicates. Blocking, refine the experimental technique, measure a concomitant variable. Covariance analysis can sometimes reduce error variance. Of course, I have to be honest, this whole slide here may not make good sense at this particular point. But of course, it will make sense as we proceed with the topic. For now, what have I said? Understand what randomization is. Understand what replication is and why do we need to replicate. Okay, let me move on to the last principle of experimental design, namely blocking. This refers to arranging the experimental units into groups called blocks, right? In each block, the units are relatively homogeneous with respect to one or more characteristics of the units that may influence the response variable. Randomization will be done independently in each block. Blocking may be based on external variable, e.g. time if the experiment is repeated over time, or observer if 2 or more people are to be used. Maybe I need to explain a bit here. Let me use a simple example in agriculture. Suppose this is a plot, a simple piece of land, and we've got 4 treatments. Call them A, B, let me have 3, and C. Now, when we talk of blocking, what we know is that the further apart you move along the land, the more variability, the more changes, non-uniformity. Why? The land here may be different in terms of fertility when compared to this one. So instead of just using this big piece of land as it is, we can subdivide it into smaller portions. So in this portion, we put 3 plots A, B, C. So the idea is to make sure that all the treatments are included in a small piece of land, and the small piece of land is usually considered to be homogeneous. Homogeneous simply means uniform with respect to fertility or all the other agronomic factors which may influence what we are going to measure. So if these are different spacing, they must be included in this small portion of land before we move here. We don't want a situation whereby we only have A variety here, and we have B variety here, and we have C variety here. That is a problem, because if A occupies this first portion, suppose that there is a high fertility here, already the differences between A and B that may be observed is not because A is different from B, but it is because A is exposed to high fertile zone compared to B, which is exposed perhaps to low fertile zone. So to avoid that, whenever we do an experiment, we will subdivide the big piece of land into smaller portions. Each smaller portion is considered to be homogeneous or uniform, so that at least all the treatments that are being tested are subjected to similar conditions to enable us to get the true differences in the treatments, not attributed to extraneous variable or intruders. So these are the three basic principles of experimental design. So what are they? Randomization, blocking, and replication. What I want you to do, go to some, you can Google the notes, you can go, of course I'll post the notes, but I want you to read on your own, understand the three principles of experimental design, and in particular the purpose that each of the experimental principles serve. What is the purpose of replicating in an experiment? Why do we need to block? Why do we need to repeat? So replication. So thank you very much. The next work that we are going to look at, I will introduce the first experimental design, which is the complete randomized design, or CRD. Thank you very much. Enjoy.